I will. Cool, how many people we got on here? Cool, we've got a number of people starting to join. Okay, so welcome everybody to R&D Fridays. I'm really excited to introduce you all to our guest speaker, Dipanj Singh from Provenio. Hope I pronounced that correctly. So hey, Dipanj.
Hello. Hi.
Okay, so just a little bit about Dipanj. Okay, come on, you guys. Sorry, we've got some last minute attendees. Okay, so a bit about Dipanj. So Dipanj is a machine learning enthusiast who loves to dabble in data science, AI, and RPA. He has 5 years of machine learning research experience and also worked as a research and machine learning teaching assistant to Professor Mike Bain at UNSW. Today, Dipanj will share some theoretical insights and practical usage of machine learning. So over to you.
Hello. Good evening, everyone. So my name is Dipanj. I've completed my master's from UNSW. I love the field of machine learning. I've been working in this field from past 6 years and researching deeply into it for past 5 years now. So currently I'm working at Provenio AI as an RPA strategist and an AI scientist. So today, as I told Kirsten, 1 hour is too short a time to cover all the topics of machine learning. So what we'll do today is go through the basics, and then maybe I can show you a code and a data set to work upon, which is like a very easy data set. And I'll show you the code as well. So let's start the presentation. All right. So I won't bore you with the basics such as the definition of machine learning and those things. I'll just straight get to the point, right? So machine learning is basically the field of study which gives computers and their own ability to think and work and provide humans insight and do calculations which is not humanly possible, right? So we can divide machine learning into 3 broad scopes that are supervised learning, unsupervised learning, and reinforcement learning. Right. So even before that, so machine learning is not just about working on the algorithms. It involves data acquisition, data cleaning, data analysis, and then you apply your algorithms on it, and then you get insights from it. Right. You get there are n types of data sets, right? The data could be in any form. It could be visual, it could be audio, it could be text, it could be numbers. Right, so they've devised 3 different subgroups into machine learning, which makes it easier for us humans to understand and make the computers work in our favor. Right, so let's say you have a data, right? And you have pictures of dogs and cats, right? So you have, let's say, 50 pictures of dogs, 50 pictures of cats, and you have marked them, right? That this one is a dog or this one is a cat. So if you apply machine learning on that kind of data set, it will be called a supervised learning. Why? Because you're providing a computer a set of data and you're providing the labels for it. Labels are the target variables which your algorithm needs to hit or find every time, right? So what I mean to say is, let's say you have a machine learning algorithm, right? The very basic example would be you have 2 kinds of pictures. One is of cats and one is of dogs. You provide them with the pictures and the labels as well. Labels, when I say labels, I mean that we have tagged each picture respectively, right? So we train our algorithm on these pictures, on these labels, and once it's ready, once it's trained, it can be used on any kind of data. Not any kind. Yes, you can say if you provide it another picture, in which it's a cat or dog, but you have not labeled it, right? that trained algorithm would be able to identify it automatically. And that algorithm would be under supervised learning. Similarly, unsupervised learning is something where you provide it with a data set, but you don't give its labels and you let the algorithm figure it out itself, which data belongs to which class. Right. And reinforcement learning is kind of like what we used to have it in our schools, right? Where teachers used to spoon feed us, and when we used to go wrong, they used to correct us. That's where the reinforcement learning comes in. It needs human interaction, where if algorithm is not performing the way it's supposed to, you intervene and you correct its course. So you reinforce it. So let's start with supervised learning. So as I said, you'll have data sets which will have n samples. OK, I'll explain it to you. It will become very clear to you. So when I mean data set, what I mean is this. So this is a very basic data set. This is like one of the easiest data sets that you could use, right? So samples mean each row in your data set, right? So what this is a data set of types of glasses, right? So your glasses have different types of chemical compositions, right? So this data set consists of 7 types of glasses and their own compositions, right? I don't remember the the exact name. Na, sodium, magnesium, aluminium, silicon, potassium, and so on, right? And if we see, we have 215 samples of these, right? 215 examples. That is what samples is, right? And when I meant labels or classes, it meant this type, right? Because these 9 chemicals identify a kind of class, right? So what kind of glass it is, that becomes your class label or your target variable, right? So you train your data on these data, like this data set, I'll call it as a labeled data set, and whatever learning we'll do on it, it will be called as supervised learning because I'm providing it with the labels that it needs to identify, right? So I have an example in this presentation. Right. So this is basically the first basic algorithm that we go for. That is regression. That is the easiest algorithm to learn and easiest algorithm to understand, which is basically plotting of your data points. If you take a 2-dimensional data set and you plot those points, right? So these points have been plotted according to your price and your square feet. So this is basically this data set is talking about your house prices. So simply, let's say if your house is 500 square feet, it will be of X price. If it's 1000 square feet, it will be of Y price. Now, if you see a data where you get a house with 1250 square feet size, what is going to be the price of it? So machine learning using supervised learning answers these kind of questions, right? So X1, Y1 is your sample, say n samples. You've plotted those n samples using regression. What we do is we find a line that best fits this set of data points, right? So as you can see, there can be multiple lines in here, right, in any which direction, but we find the line with the best fit. And that is, you find that line with the best fit using a loss function. Right, that is a topic for another time. Right, now in that example, we were talking about a data set with just 2 features, right? This one, let's say if you have 3 features, you'll have a 3-dimensional graph. Yes, now features. So if I was talking about features, these chemicals would be called as features of a glass, right? Because they tell you which kind of glass it is. So these are what features. Similarly, in our example, house price, size, location, these will all be called features. Right. So if you have high dimensional features, if you're talking about the glass data set, X1 would be the RINAKCA. Similarly, you'll have the points, and those numbers are basically defining what kind of glass you're looking at or you want to classify. Right. Now you have regression. That is what I was talking about, where you predict. So regression, one thing to keep in mind is regression is used on continuous data. So regression is best used for, let's say, if you want to predict a stock price, if you want to predict the price of Bitcoin in, like, let's say 3 years, right? You would use regression for it. Regression would be one of the best fits to go for because you have that data regarding your old price fluctuations, and you can use that data to predict the price in the future. And this is one of the basic algorithms in machine learning. Then so computer vision. So now, as I said, machine learning is just not about your numerical data, right? It involves computer vision, it involves image segmentation, AI would include your robotics and all those things, right? So in your computer vision, as I said, we were talking about cats and dogs and we were labeling the picture. What I meant by labeling the picture was, as you see in this, right? While we're training our algorithm, our computer vision algorithm, that would be the best one I would say would be convolution neural nets. And I'm currently working using convolution neural nets, and you could search YOLO. That is you only look once concept in computer vision. That's also a unique concept. So basically you're tagging these pictures, right? I've tagged this picture saying that these 3 objects are kite fox. And I train my algorithm with thousands of such pictures. And after the training, I provide one such picture to it and let it identify. If the training is done enough, and there is another buzzword called if our model has converged, that means it will be able to predict a real life data up to an accuracy that it shows. Right, we'll talk about accuracy as well. So natural language processing, as you'd seen, Google Translator is one of the best natural language processing system out in the world with using the alphabet, right? So this side is also a branch in machine learning, which is called deep learning, which includes NLP, your computer vision. What else? Yeah, AI would include, because these are using your basic machine learning algorithms and piling them on top of each other to form a complex algorithm to solve your purpose. Right. Then you come to unsupervised learning. Unsupervised learning is, let's say, I've given you a set of let's say I've given you a set of data which would tell you that, okay, yeah, so let's say, let's take the example of your table and your chairs, right? So your table has 4 legs and a top, whereas your chair has 4 legs, a top and a back as well, right? So you have these 2 kind of data sets, but you don't have their labels for it. And you let the algorithm figure it out on itself that if this is a chair or a table, right? So dataset contains no labels basically. So yeah, as in this example, as you can see, a difference between a house and a townhouse. So you have provided its 2 features that I would say a lot size and a price, and let the algorithm figure on its own whether it's a townhouse or a house. And this kind of learning is called unsupervised learning. Okay, so clustering is one of the examples in your unsupervised learning, where you let the data points cluster on its own because the same kind of data would stick together, right? As you can see in this, if I make clusters out of it, and it has a 9-dimensional data plane, like for type 1, it's a sorted data set. That's why it's this way. If it had been unsorted, yeah, if it had been unsorted, this would have been totally jumbled. I'd sorted it out to ease the usage, basically. So as you can see, all these data points will be close together in your 9-dimensional data plane. Similarly, if you go for type 2, all these data points would be somewhere close together in your data plane. So yes, if I don't give the labels to our unsupervised algorithm, that would be, let's say, clustering, it would automatically give the labels out to you. Okay, that this set of group is one type of class. This set of group of data points is one set of class. And there is one problem that you might encounter that was outliers. Outliers are basically you have data points sticking together, right? And you have one data point going outside the rest, right? That is called an outlier. So these are like, it's showing that it forms 3 clusters, and basically clustering algorithm, you give the number of classes you want to divide it into. If I want to divide it into 7, it will form 7 such clusters. As I've given it like 2, so it has formed just 2 clusters. That is the townhouse and your normal houses. Right, so it is used in genes, and unsupervised learning is mostly used in your bioinformatics, right? Then your LSA, latent semantic analysis, that what kind of words are in which kind of documents and where do you find those? Right, and this is word embeddings, where you have to, where you convert your words basically to vectors, which become easier to use in the long run, because you have, like, this data set that I'm showing you is just 215 samples, but in real life you get millions and millions of lines of data, and the computing power that we have in our laptops are not sufficient for it. So what they've done is they've cut down data sets for a short, for us to use for simplicity of usage, right? So clustering of words is another thing where unsupervised learning comes into play, right? Where it would cluster it on basis of, let's say, emotions, or here they have clustered on the basis of logic, graph theory, particle physics, polymer, etc. Right, so this is what clustering would look like. So it clusters the word together to divide it into different classes. Then you have reinforcement learning, where you teach, it's basically reward system. If it does something right, we give it a reward. If it does something wrong, we tell it to correct it. So this is basically the number of iteration it takes for it to learning to walk. This is a reinforcement learning algorithm. So at 10 iterations, that is, the algorithm has been trained on data 10 times only, would result to this. But as you see, we increase the iterations, and as we see that on 10th iteration, it's falling down, we correct it. So by 20th iteration, what we get is somewhat like this. Little better, it's taking a couple of more steps and then falling down. So this is the very basic idea of reinforcement learning, where you teach bots, like your robots that work in your labs, the human bots that are being made, they all work on natural language processing, natural semantic analysis, and reinforcement learning. So by 210 iterations, as you see, it's starting to learning to walk. And that means the algorithm is converging slowly to a target point. Right. So this was the taxonomy. We have just been able to scratch the surface, and this is what you look forward to when you go deep diving into machine learning. There is a lot of maths involved, which I've not covered in this lecture. Then there is deep learning, wherein you learn the supervised, unsupervised, and reinforcement learning from basics, and then you dive into deep learning, which will include neural nets, convolution neural nets, long short-term memory, LSTMs, etc. You might have heard of these buzzwords, but they all come under deep learning. And deep learning is basically teaching the computer to think the way a human mind works, right? As you can see from this diagram, this is a set of a neural network. So neural network works the same way our neurons work in our brain, right? They pass electronic signals to each other to relay a message. Similarly here, one neuron passes on a message to the next neuron, all four, and similarly to find out what the message was. Then there is a feature selection. Feature selection is basically like in this data set, you just have a set of 9 features which are doable with our computing power. But few of the data sets include 500 set of features. Like I remember I was working with a data set that had 1,000 features. Now explaining a thing with 1,000 things won't make it easier than explaining the same thing using those 10 exclusive features that define it, right? And that's what feature selection is. So if I'm talking about a chair, it won't help someone to understand that it has wheels, it has 4 spokes or something like that, which are redundant, and we don't want that. And for that, we need feature selection. There are automatically inbuilt algorithms in machine learning now, which makes it so much easier nowadays. Like when I was doing the research 5 years back, there weren't such exclusive libraries for it and neither the computation power. But nowadays it's just 10 lines of code and you get your answers, and I'll show you. Right, so let's go to our code. So yeah, the IDE that I prefer and I use is Anaconda for it. Right, let's open our notebook. So let's see. Okay, let's open our notebook here. I've already created a notebook, but I'll go through it. As you'll see how various libraries and various toolkits such as scikit-learn, Tableau, not Tableau, but TensorFlow, they have made machine learning so much easier now that if you just want to work on a data set and work using codes, it has become very easy, right? So we'll be using the same data set, that is the glass data set, right? And we'll be creating a machine learning algorithm basically to predict if we provide it with a set of data, right? If we provide it with a set of data, will it be able to figure out what kind of glass it is or not, right? So number one thing would be importing our important libraries. So important libraries that you would use with it is NumPy, Pandas. These are libraries which are very helpful for data wrangling, data collection, data modification, and data cleaning, right? So I would say if you want to start with machine learning, I would say go through these 2 libraries first, and you get the gist of what you'd be working on and what kind of data sets you might inquire, and what kind of data sets you might get and what kind of modifications you'd need to do, right? And then there are few scikit-learn libraries that I've used here that I'll explain, right? The number one thing would be reading our Excel file. So if you've worked on Python before, reading a file is basically 4 or 5 lines of code easily, right? Now Pandas has made it that much easier. You just have to read CSV. As I've declared Pandas, that is a library as a PD variable. I'm using it directly and its functions to read our Excel file. So let's start. And this is a Jupyter notebook that I've been using. This basically lets you run your lines of code. Yeah. So all our libraries have been imported to a data set. You could use other IDs as well. This is the best notebook for basically explaining a code or running your code line by line, right? The number one thing I do is read our data set. So our data set is read, and if you want to see what a data set looks like, so we can see, let's add another line of code here. Dataset dot head, which would show us the top 5 lines of our dataset. That is, these are the features. This is the type that we have to find, right? So this, now I divide our dataset into 2 parts, right? That is, I'm just leaving out the last type because we need to predict that. That is our target variable, and that I take it in y as a y variable, right? So we have x and y. X includes all your data, and y includes all your target variables. Now, when we provide these 2 variables to our algorithm, what it does is it works on the data that we have provided, and it tries to predict a number close to our label set, right? So let's say I provide the first line, all these 9 values to our algorithm, and let it predict. Let's say it predicted that it is type 2. And I see, okay, that the prediction should have been type 1, but instead the algorithm has predicted that it is type 2. That means it's not working correctly. That's where the loss function comes in, which is basically the difference between your target variable and your predicted variable. Because what needs to happen is your algorithm needs to correct itself. And how does it correct itself? It sees the difference between what it needed to achieve and what it has achieved, right? So I've divided it into 2 parts, that is our data and our target variables. Now, as it's only 215 lines and the data set has not been divided, and okay, how do we know that our algorithm is working correctly or not? So one set we use as a training set where we train our data, our algorithm, and one set is used as your test set, right? Test set gives you basically the accuracy that on the data that algorithm has not seen before, right? So if I provide it with 215 data all together right now, it won't be able to tell you how accurate it is. To tell you how accurate it is, we give it a test set as well, which tests the algorithm, and you get to know, okay, this is the accuracy of algorithm. And if you're not satisfied, you do the training again, you add more data, you reduce the features or you increase the features depending on your output, right? So now, instead of splitting it manually, I let sklearn do the job for me. So I import sklearn.model selection train test split. This basically randomly splits your data set into the size that you give, right? If I give your test size as 0.30, it will divide the 215 data. It will take randomly 30% of the data outside and make a test set out of it. That's what we need. Instead of like us creating lines of code to select individual data or select data randomly, we let sklearn do the job for us, right? So let's say I'm taking 30% data for test size this time, and random state is basically how randomly it will take. You can give any number you want. I'll give 412 here as well. Okay, so let us divide the data into our train. Oh, I haven't run this block. So I haven't divided our data set into our training and test label that I've done. Now I'll go with the train test split. Now this has divided into an X train, Y train. These 2 labels will be used for training, X train and Y train. X test and Y test will be used as a testing set to test our algorithm. Right. Now, one more important thing. As you can see, these values vary from 0 to 80, right? There is no standardized set of values. These are not standardized set of values. So how our algorithm could work on this data set, but it is not suggested in general practice of data science that you let the data be so vary, because if you find the standard deviation of it, it will be so huge. Instead of that, what we do is we standardize our data set. And again, letting the sklearn dataset do its job, we import a standard scalar function from sklearn.preprocessing, and we scale the dataset between 0 and 1, which makes our algorithm work faster and more accurate. Right. So I've called the function here, created a variable, then sent our training set and our test set. We don't send our labels because we don't have to normalize our labels, because that is what we have to predict. So we send our testing and training data for standardization. Now this has been standardized. Now we were talking about regression as one of the algorithms, and I said that regression is best used when your data is continuous, right? But here what we need to do is we need to classify our data into 7 different classes. So I've used one of the fastest and one of the strongest machine learning algorithm out there, that is random forest classifier. If you read through machine learning, you would learn that this is an ensemble method. An ensemble method is basically using various machine learning algorithms, or using one very basic machine learning algorithm and building on top of it. So a very basic machine learning algorithm is a decision tree. So decision tree is basically a tree which is basically, if it's raining, there are only 2 options, that you can either go to play cricket or not go to play cricket, right? So this is what a decision tree is, where branches tells your decision and your leaf roots are basically your what you had to do, what decision you had to make, right? So random forest uses, and in machine learning, it is said that it is a weak learner. A decision tree is a weak learner because it needs a lot of training and a lot of data to make useful insights. So what random forest does is it creates a forest of such trees. It uses, like right now I'm using, like I've declared n estimators as 300. That means I'm using 300 such small decision trees working together on the same data to make the prediction. I can increase these estimators as well. Let's use 500 decision trees. You can use as many as you like, but it's not suggested as you have limited computation power. And after a while, it's said that if you use something too much, you won't get anything out of it. If I use 1000, where my job could have been my thing could have been done with like 500 trees, then why go with 1000, right? So I import now again. Instead of creating a tree, if you worked in C or C++, I used to hate trees, and in data structure especially. This does your job so much easier. It creates those trees, it fits your data on it, and it just presents you, okay, this is your answer, here you go. All right, so I import that function here, that is the random forest classifier, and I call .fit on it. So .fit means .fit is an inbuilt function that is present in random forest algorithm, right? What it does is it's basically training your random forest algorithm on X-train and Y-train. X-train was again your training data set, and your Y-train was your training labels, right? So what this here is doing is it's basically training your random forest on 70%, because I divided into 30, 70% of your data, and trying to predict the outcome. And as soon as it predicts, it matches with the Y train, that is your labels. And if there is a mistake, it's sent back to training again. Let's run this. It's going to take some time because I'm using 500 small decision trees here. Oh, it's been done. Now, as you see, I've declared this variable CLS here. Using cls.fit, I've trained our algorithm. Now I have to find out how accurate our algorithm is. Right. For that, I use cls.score. Now .score is another inbuilt machine learning function, which is used to tell an accuracy of an algorithm. right? So let's try this. Our accuracy actually decreased because I'm giving it a smaller set and using a lot more estimators. Now let's try and give it a 20% test set and 30% training set, 80% training set, and you'll see that this training accuracy increases. This is the type of fluctuation you'd need to do, and this is what brute force, or not exactly brute force, but yeah, testing again and again and again to make it right. Right, so let's use 300 estimators while making our test set as 20%. Let's run the algorithm again. It's run, and now let's find out our accuracy. In our last run, our accuracy was 78%. It's increased to 79% now. So this means this accuracy is basically whichever new data I'll provide, it will be able to accurately predict the class 79% of the time, right? So this model is now created. It has now been trained. It has now been like stored. It is stored in CLS. Now, this is just the basic of your machine learning, where you've read the data, you've cleaned the data, you've divided the data set into your training and testing, and you've trained your algorithm, and you haven't tested it yet. We need to test it, right? But before that, what I do is I save my model. I save my model and I dump it. So again, joblib is another library which dumps your model. This has saved our model as finalized model.save, which can be used in your web applications, in your different frameworks. Like if you want to create a website which inputs a data and you want your website to basically predict the data set live. So what you do is you train your algorithm on a set of data set, you save your model and you use that model every time while making predictions online, right? So now I can load that data set, that algorithm again using joblib.load. This is the same function that you'll use if you're using Flask or Django, right, to create a website, or you can use the same .save file in your mobile applications, building mobile applications, right? So let's load the model. OK, I've loaded the model now. Now what we need to do is for testing that if our model is accurate or not, we need to provide it with a data that it has not seen before, right? So as you see, these are the seven types of classes that are there, that building window, float process, etc. These are the 7 different types of classes basically. If you see headlamps, tableware, containers, etc. right, which have different types of compositions. Now let's take an input from our line. Like, so it's asking me to provide it's asking me to provide the value of Ri, right? So I'll give it a random value, let's say 1.52 NA, and I'm trying to give the values in the same range itself that it has seen before, right? Let's give the value of NA as 12, MG as 3, SI as AL. I've given just random values. I have no clue what I'm entering, right? Let's enter the value of iron as 0. OK, so it has input the data. This is your data, and now we need to make prediction using our trained random forest, right? And for that, we again use an inbuilt function that is cls.predict. Using this predict, I've input the list here in your predict function. That means I'm sending the data, this data, that is these 9 values, to a random forest to make its prediction and tell us which kind of glass data set it is. Right, now I have stored it in answer and I've printed out. The prediction is 7. That means this kind of composition in any glass would mean that it is an headlamp. And that is what your simple basic machine learning algorithm looks like. And you can basically use this in various places. Now, if you want to see, we can try regression as well. Import, I don't remember the class. sklearn regression. As you see, there are very well documented libraries out there for machine learning, which makes it really easy to research, really easy to learn and understand, right? As we were going on about our linear models, that was your regression to predict your Bitcoin or your house pricing or your stock prices. This is the best place to go to learn about it, basically. So I need to import a linear model. Let's import a linear model. Right. And using this linear model, we can call our regression. Right here. So removing this core, let's create our regression. Now this basically calls your regression function that is inbuilt sklearn function, and it creates the backbone of your regression, right? I'll have to run this again. sklearn done. Now let's run this again. That is also done. Now what we need to do is, number one, we need to fit our data, right? That means we need to train our regression function on our data set. That is pre-divided, that is X-train and Y-train. So that has been done. I'm using a very basic linear regression out here, not anything complex. Let's try and see what accuracy we achieved in here. Oh, 79. Oh no, sorry. Yeah, see, 47. As I said, this data set is very small and it's not continuous, so regression won't work really well on it. So as you can see, 47% is not acceptable. That means like half of the time it will be making wrong predictions for us, right? We can add more features here to make it work better, right? Like we can add entropy. If your data set is small, we can add a few like alpha here. Alpha works, which would increase its accuracy. Alpha or dot ridge. But it won't make that much of a difference because our data set is not continuous and we have too less of a data here. So the best algorithm that would work is regression trees. And if I say 80% is not good for regression trees are meant to hit an accuracy of 90 and above because they are very strong learners, right? So for various data sets, you can always go to Kaggle, right? Kaggle is one of the free hostings for your different data sets to try out, to learn, and to work them. They host different competitions as well, where you can use their data sets for free, and you can enroll for their competitions as well, which is a very good place to learn and to know about the latest machine learning algorithms. So that would be all for today. Any questions?
Yep, I've got one question, Deepanj. So I'm guessing you've heard of that one course from Andrew Ng, the Stanford.
Yeah.
Like just so that's like a decade old. would you say there's anything new happening? Should I be relearning any of the maths behind it, or is that still fine?
See, one of the deep learning specialization by Andrew Ng is one of the best courses on machine learning out there. I've completed that as well as a specialization. Yeah. It's a MicroMasters specialization, and it gives you such beautiful insights in your latest, not even latest, but the basic technologies that you would require, right, to ace machine learning basically, because it gives you the hands-on experience as well with its assignments. And Andrew Ng is one of the best teachers out there, in my opinion. So generally, if I say like the maths behind machine learning doesn't change much, not even much, it doesn't even change, because your neural nets have been there for 60 years now. Geoffrey Hinton, the father of neural networks, he's currently teaching at University of in Canada, Waterloo, I think, and he's like one of my biggest inspirations. And he even said like the maths behind it, the stats, they do not vary much. But if you ace that once, you'll be good to go, because your new technologies, your new machine learning technologies and your algorithms are built on top of your older algorithms. If you clear your basic with the older ones, you're good to go. Nothing new will be as enticing or intimidating. It'll be very simple.
Yep. So I've got another question. So obviously with gradient descent, you're going through like every single regressor, and for every single regressor, you're going through every single row of that data set. So it's a bit like very computationally expensive. I'm just wondering, like with a model that's pretty complicated, so like say 100 features and some of them go to powers of 2 or 3. How would you run this? Like, what would you prefer running this on? Like in the cloud, or like what sort of a library would you use for this?
See, if your training is taking too long, and by too long I would mean because like for a data scientist working on their own laptop on a big data set, if it's taking like more than 3-4 hours, that means either the data is too big or you don't have that much of a computation power. So if you don't have it, there are a couple of options that you could try. There is Google Colab, COLAB, because they provide free GPUs, but not a high tier one. They provide a Tesla T4 GPU, which is obviously faster than the one that you have in your laptop. I use that generally, and there is Google Colab Pro, which is I think $10 a month, which gives you really good computation power. Different GPUs they provide, different TPUs they provide, so you could go for that. And apart from that, if you can get your hands on EC2 servers, what's better than that?
Yeah, sure. Yeah, like sorry, I have like more questions as well. I don't know if anybody else wants to. Yeah. So just one other thing. So you obviously talked about like scikit and like all these other very high level machine learning libraries. Yeah. So I think the latest one is PyTorch. So for someone, it's not really the latest, but it's growing in, I guess, usage. I'm just wondering, like, say if like what do people in your field use, or like what are they comfortable with, and where do you see people going?
See, PyTorch, TensorFlow, I've used these libraries, but I've used them majorly in deep learning, not in basic machine learning. You don't need PyTorch because you don't need tensors, and they basically, I would say TensorFlow provides you threading options, right? PyTorch is equivalent to scikit. Scikit, I've been using it for like 5-6 years now, so I'm really comfortable with it. PyTorch is very well used in neural networks. In your deep learning frameworks, I've seen it mostly, but yeah, I would say master all of those, like even TensorFlow. It's way better than PyTorch and scikit.
Yep, fair enough. Yeah, and just a last question. Say with like ResNet, so for vision learning and whatever they call it. How exactly, like when you look at the like the not the input or the output layer, those parts are easy to understand, but the middle layer, how do you understand the complexity of the model? Like it just doesn't make sense.
Convolution layers and the pooling layers, all those things. Yeah, those are for those you need to deep dive into computer vision and deep dive into convolution neural nets. Start with neural nets, right? Because neural nets do not work on your pictures, but they make you understand the workings behind it. Like even your convolution neural net uses I forgot the name, back propagation,
Yeah, that's right. Yeah.
And that is the basic of back propagation comes for your neural nets. If you've understood the maths behind back propagation, which is like one of the most complex algorithms out there in machine learning, right? You'd understand convolution neural nets. But for convolution neural nets, I think deep learning specialization only by Andrew Ng, and the fourth course is on a deep this convolution neural nets, where he teaches you about convolution layers, your pooling layers very beautifully. That's where I learned it from, and then I did a subject which made it much more clearer for me.
Yep. Sweet.
So yeah, just imagine instead of in 2D, just imagine every layer in 3 dimensions. That would help you a bit, but I would say go with the maths before.
Yep. And this is probably like my last question. Say, for example, like an engineer would like to go into, data science, or like I think data engineering. I don't know the difference. Sorry. Like, what exactly should they know? Like, if you know the majority of the maths for, basic neural networks and machine learning, so gradient descent, the cost functions, least squares, all that stuff. I guess that's just the basics, but would that be enough to get a job in? Yeah.
These a job. I was thinking about a course. Like, you want to do a data science course, or you want to go for the data science job?
So, like, my question is, like in the interview, like, what exactly would they ask? Is it very maths heavy, or is it?
They do ask a lot of probability. They do hit up on the buzzwords that you regularly hear in machine learning, right? They would ask very like basic questions. They won't deep dive into, like, they won't ask you to explain a convolution layer, etc., until unless you're applying for a computer vision analyst or something like that. Right, but they would definitely ask you a difference between a logistic regression and linear regression. Right.
Yeah, that's
so
pretty
this
simple.
is like yeah. So these are the basics that you need to work upon, and you need to ace it in order to get a data science job.
Is there perhaps a course, Dipanj, you could recommend to Hanif if this is something he's wanting?
I've already gone through it, so it's fine.
Oh. Okay.
Yeah, the course, another one that I've done.
Anyone else, perhaps in this? Well, you could send me some information if you're.
Yeah, I would. Let me just send you a text not a message.
I don't need to do it right now, Dipanj. You can do it after.
Yeah, I'm sending you guys a link where basically I teach the basics of computer vision, not computer vision, but machine learning in total. If you guys want to get some insights or deep dive into the maths, right? You can go on this and try it. Just give me a second. Yeah. Any other questions? Meanwhile, I'll send you the link.
I think Ricardo had a question, if he's still on. Didn't Ricardo? Oh, maybe he had to jump.
Sorry, no, I was on mute. Sorry about that. Yes, I do have a question. It's more like a historical thing, and I'd like to see if you can shed some. It's just a curiosity that I have. I mean, I have been around some other projects in terms of machine learning, and the data scientist that was involved, I mean, she actually worked quite a lot with Python. Okay, And there were some cases where I needed to help her a little bit because, you know, the Python couldn't perform some calculations fast enough, and I had to write a couple of examples in C++. Is there a thing like why Python is so prevalent in this kind of a data sciences field?
Python is more prevalent because it's more of a high-level language, right? So like this, the data that I showed you and the code that I did, we completed it in within 10 lines, right?
Right.
If I don't go with the libraries, because yeah, number one thing, Python, there are n number of libraries available for machine learning, right? It is not so with C, C++, and Java. So in order to like, let's say you wanna, like, I know they've provided some libraries for Java now, but I don't think there are any libraries in C or C++ that could do the job that you could do in one line in Python. And the other thing is, with C, C++, and Java, I feel you'd be only declaring variables all day long, and you'd be getting an exception error. But with Python, it all handles it all by itself. It lets you do the higher level job. That's why it's more prevalent.
So there is no history behind because certain things start a certain way, and because, you know, things are always done like this.
No.
Have all these libraries for Python. Is it because, you know, it's also very heavily used in the academic world as well?
Yep, and like you have such a huge community that you get most of the answers, right? If you go with, like, let's say you want to do regression or like regression with Java, even if you go and Google it now, I don't suppose you'd get any resources for it. Not even on Stack Overflow. I've never done that. I don't like Java, to be honest. I'm sorry, but I'm more of a Python guy. But yeah.
So basically, as a conclusion for our, you know, my pseudo question is that if you want to play with machine learning, Python is going to be the right tool for you to use.
Yeah.
Also, Ricardo, just for an FYI, a lot of the core for like TensorFlow and those other libraries are written sort of in CUDA for GPU stuff and for C++ for the intense compute stuff. So it does have a lot of the speed of C++ and above.
Right.
Because yeah, Python itself is built upon on those languages. So it easily can use those libraries and makes your implementation much more faster. And much more less error prone as well.
Right. I was not suggesting that there would be a more appropriate language to do this in. I just want to know if there was a history behind.
No. Like there are nowadays like Go, R, MATLAB is also even used for machine learning.
Right.
There are n number of languages, yeah. But it's nothing related historically or something. It's just the community. The community built itself around Python. And that's how it continued.
Right.
And for anyone who's an ace in C, C++, and Java, Python is a piece of cake anyways. It's very simple. It's very straightforward.
Yeah, I mean, I did play a little bit with Python. The only thing that brought me a little bit of an issue was that you have, you know, indentation is not just for looks, right? Indentation is a component of the language, right?
Sorry, I didn't get you. There was
when you have to indent something to for certain statements to work correctly. Is that right?
I'm so sorry. I didn't get you.
That you have to.
There's a disturbance. Hello.
Perhaps you're not hearing me. Correct.
Yeah, I'm so sorry. Could you go again? I'm so sorry.
Yeah, that's okay.
Your birdies in the background.
Yeah, I could hear some tweeting in the background.
Oh, no, the birds now are coming. You know, after a long day, they're coming back to sleep. So there's a lot of trees around where I live, so they sleep there. So Python, one characteristic that I saw that do you have to indent items on a second line on lines for them to be in the right syntax form?
Yeah, there is indentation required, like especially when you're using loops and defining functions in classes. Yes,
Yeah, well, let me tell you this. I started in computer science a long time ago, and the first commercial program that I wrote when I was an intern at university, I had to use COBOL. And COBOL also, there are very strict rules on indentation, and I absolutely hated it.
Yeah, no. If you know C, C++, and Java, you'll love Python.
Yeah,
And
Python's a great
you
language.
won't ever use C, C++. Like even during my masters, they made us use C for data structures, and I totally hated it.
Yeah, that's right. And one final question before I pass the microphone for someone to ask more questions is that are there rules, for example, of what kind of volume of data that you need to get accurate predictions?
Nothing as such. As you could see, like we were only using 200 lines of data to make a prediction out of it, and we were able to get our algorithm up to 80% accuracy. Right. Now it's easier for algorithms to reach a certain level, right? Like after 200, if I give it 200 more data, that is like 400 lines of data, it doesn't mean that it will reach the accuracy of 95%. It will just increase the accuracy now 1%, 2%, and so on. It will like slowly increase. So as much data that you can provide, it's beneficial for your algorithm. It gets to train more, it becomes more accurate. But the minimum level, as you could see with regression, it was a minimum level. We need more data for it, at least to make an honest prediction out of it.
Right. All right, that's what I had to ask. Someone else now.
Ricardo and Hanif have been your favorite attendees today. Any more questions from either of you before I pass it on to anyone else?
No, not for me. Thank you very much for answering our questions.
No worries.
Any other questions? No. No. Cool.
All right. So.
Okay. Well, I think.
Meanwhile, I'll just share my playlist link with you, which I've created, which has like some basic machine learning videos, which go through a few examples. It's not code, but it shows the math behind it, basically.
Can I ask one final question? I promise.
Yeah, no worries. Just go ahead, shoot.
I promise. Will quantum computing actually do anything special for machine learning?
Quantum computing, like what do you want to say as like quantum computing?
For example, if you get the algorithm that we have today, I mean, will quantum computing allow us to create, better predictions with less data, or run them faster, or actually produce some results that that's closer to the human brain? In other words, will we get
because quantum computing would let you compute more data in less time, right? I would definitely say it would make your algorithms much more faster, and faster the algorithm, you can train more data on it, right? Where like on your computer, if you say like train 1,000 lines of data, while on quantum computers, you can train 1 million lines of data in the same amount of time, then obviously your algorithms will become much more accurate. Right, and especially like CUDA, the parallel processing part, that is helping machine learning a lot right now, especially like TensorFlow and all those libraries. They are proving a difference.
Right. Thank you. And I promise that was the last question. That's it.
No, we can go ahead.
We love your questions.
Yes, I do.
I thought Woody might have had one, but perhaps he's had to log off. Is there any other questions from anyone? Okay. Well, Dipanch, this has been really enjoyable and really informative, and thank you so much for joining us today. You're obviously very experienced in what you do, and if anyone has any questions for Dipanch after this, please send me a message, and or connect with Dipanch on LinkedIn.
Definitely.
That's how I found them.
And thank you so much, guys, for listening to me patiently. I know I can go on about machine learning. And as I was talking to Kirsten, and I told her like 1 hour, I would only be able to scratch the surface because I can go on on about machine learning for days.
You're more than welcome to come back. Step 2, stage 2.
Stage 2, chapter 2.
Yeah.
So guys, I've shared the link with you. Feel free to go through those videos. I hope they're kind of informative for you. These were made during my master's when I was working as a tutor. So let's hope you find them informative.
Thank you very much.
Thank you.
Awesome.
Really appreciate it and taking the time, to speak with our team. So
It's lovely to talk to you guys.
yeah.
That was awesome.
Thank you.
Thank you.
Have a good weekend.
You too, guys. Bye-bye.
Bye-bye.
Thanks, Deepak.